Hello everyone, I'm Prof. Priya. This is the third video in our 10-part series on quantum computing. Previously, we studied the linear algebra foundations. Today, we explore the fundamental unit of quantum information, the qubit.
Professor, I know classical bits can be 0 or 1, but what exactly makes a qubit special?
Great question, Sneha. A qubit is represented as psi equals alpha times state 0 plus beta times state 1. Unlike classical bits, qubits can exist in a superposition of both 0 and 1 simultaneously.
Professor, what do these alpha and beta coefficients actually represent? Can they be any numbers we want?
Excellent question, Arjun. Alpha and beta are complex numbers called probability amplitudes. They must satisfy the normalization condition. The magnitude of alpha squared plus the magnitude of beta squared equals 1. Now here's where quantum mechanics gets fascinating. When we measure a qubit, the superposition collapses. We get state 0 with probability alpha squared and state 1 with probability beta squared.
Wait, so quantum measurement is fundamentally random? We can only predict probabilities, not exact outcomes.
Exactly right. This follows Born's rule. Now, let me show you a beautiful way to visualize qubits. Any qubit state can be represented as a point on the surface of a sphere called the Bloch sphere.
This sphere is amazing. What do the north and south poles represent? And what about points on the equator?
Great observation. The North Pole represents the 0 state, the South Pole represents the 1 state. Points on the equator represent equal superpositions, while theta and phi angles define any point on the sphere.
Professor, what happens when we have multiple qubits? Do 2 qubits just give us 4 possible combinations?
That's where quantum mechanics gets truly exotic. 2 qubits can form entangled states like this Bell state. Phos equals the sum of 0, 0 and 1, 1 divided by root 2. This cannot be written as separate individual qubits.
Wait, so these qubits are somehow connected even when separated? Measuring one instantly affects the other? This seems to defy classical physics.
You're absolutely right to be amazed. Einstein called this spooky action at a distance. Entanglement is purely quantum mechanical. There's no classical equivalent. It's what gives quantum computers their power. Let's summarize our key concepts. Qubits are complex superpositions of 0 and 1 states. Measurement probabilities follow Born's rule. The Bloch sphere gives us geometric intuition, and entanglement is uniquely quantum mechanical.
This has been fascinating. What will we learn next? How do we actually manipulate and use these qubits?
Excellent question. Next, we will learn how to manipulate qubits using quantum gates and circuits. We'll see how to perform operations like rotations on the Bloch sphere and create quantum algorithms. Thank you for joining us.